All right. I think it's recording now. Right? Yeah. So we were talking about energy methods before we have the midterm. We're talking about energy methods, and we said, well, I should have brought the slides, so let me go over those slides. And we said, well, in Newton's approach, or well, direct approach, sometimes you can even refer to that, is that we were looking for the relationship between acceleration and the force. So external forces applied to our system, and how do they affect our system? How does our system accelerate under the effect of those external forces? Right? Now, from Newton's method, we can actually derive energy method, although that did not that was not done by Newton. It was done later on. We can derive energy methods, or the equation that we use to find the relationship between change in position and change in velocity for a system, which basically what constitutes energy methods, or what is the gist of energy method, if I want to, well, gist probably is not the right word. What we do when we are using energy methods, basically. We came up with a general relationship. We said, well, work done, and this is basically the principle of, I mentioned that, it's the principle of work and energy, and what it says, this equation in red box, it says work done when the particle, in this case we're still talking about particle, we'll see this actually can be extended to rigid bodies. I don't think in this course I've ever had a chance to talk about energy methods in studying rigid bodies, but when we're studying particles, basically work done as the mass, or whatever mass we're studying or object we're studying, moves from 1 to 2 is equal to change in kinetic energy, right, in that, during that motion. Now, we talked about the right side is not really that complicated, just especially when we're dealing with particles, as long as you know the mass of the particle, the systems we're dealing with, the mass is not changing, and that's why we could go from the equation above that red box to the final expression, or the one above that, basically. Mass is not changing, so mass is fixed. As long as we know the velocity at the beginning and at the end of the motion, we are good to go. Or maybe one of them is unknown, we're trying to find the other one. The left side is the tricky part that we have to be careful when we are working with that. Now, for the left side, which we basically represented it with U, work done, I gave you some information about the left side, basically. We talked about the left side of the equation. I said, well, remember, first of all, the left side is a dot product, meaning that we care about the direction or the angle formed between the force or the resultant force, summation of forces, the resultant force, and the direction of the motion, right? The direction that the motion is happening. So since it's dot product, it basically is the magnitude of both multiplied by the cosine, the angle of the angle formed between these two directions. So that we have to keep in mind when we're dealing with forces and we're finding the force done by work done by a force or a resultant force. And we said this also tells us when the force is perpendicular to the path, well, that force doesn't do any work. Right? And that happens especially in the case of tangent normal coordinate system. We said, well, if you decompose your forces into tangent normal forces, the normal forces don't do any work. Then we talked about two particular forces that we're going to deal with very frequently. So the left side, we have that integral form, but there are two cases that we can simplify that into just some straightforward expression. Right? One was work done by gravity, and we said, well, that's basically minus mg delta h, and the whole expression, I just emphasize on that it should be negative if the height increases, and it should be positive if the height decreases. And the reason I emphasize on this, because in the next class we're going to start talking about conservation of energy, and the form, the concepts are the same. We just get rid of non-conservative forces. We'll talk about it in that class. And positive and negative signs, can be a little tricky. In this case, remember, negative, if the height increases, when you do your calculation, you just look at the result and make sure that the final result is negative if the height increases and is positive if the height decreases. That was for gravity. Also, we talked about the work done by spring, another specific kind of force or work done by a specific force that we care about or we deal with very frequently is that one, should be negative, guys. If you please in your note fix this. Apparently I missed it. This should be negative here, minus, right? Great start. I was talking about positive and negative. There you go, I missed one. So this is minus 1 over 2k. Just go back to your notes. If you're taking notes, make sure that negative is there. Minus 1 over 2k, S2 squared minus S1 squared. Now, k is the spring stiffness. You've seen this before. In statics, is Newton per meter or pound per inch or any unit for force divided by any unit for length we have. As long as units are compatible in the general equation. And S1 and S2 are values of the strength, a stretch. Right, no, stretch of a spring. So whatever the spring is, how much is the spring is stretched or compressed. Maybe I should add stretched, value of stretch or compression. It's the best I can, maybe grammatically. Compression of a spring. So if the spring is not stretched or compressed, the S value is 0. If it's stretched, you just find how much is stretched or compressed, and that would be the value of S, depending on how much is stretched or compressed at point A and how much is stretched or compressed at point B when you're looking at the motion between the between 2 points. So as long as you know that this and you know the stiffness of the spring, you can calculate work done by spring. Now we were going over one example. We did this example, I believe. We started this one, and somehow I don't remember where, but I got lost somewhere. So I'm going to try it again today. Hopefully today is a better day to solve this problem. For solving this problem. All right, so hopefully you have this problem somewhere in your notes. We have a spring, we have a mass attached to a spring on a sloping surface. The problem statement tells us that we push the mass up to some position s equals to -1, s being the origin as is represented on this figure or the graph. Figure is good. We go 1 unit up, -1 meter, and then we'll release this mass on this smooth surface, so there is no friction involved. And what we're asked to do is what is the magnitude of velocity when it is in position s equals to 0. So it goes up, we push it up, so the spring is stretched because the spring is unstretched when s is equal to 0. So if we go up 1 unit, the spring is compressed, sorry, not it's compressed. We let it go. Because of the spring force and the gravity, it starts sliding down or starts accelerating downward. Now, what we care about is that we want to know what is the velocity of this mass when it passes s equal to 0, right? When it comes down 1 unit along that sloping surface. All right, so starting with the general equation, we had U from 1 to 2, right? The work done on the system from 1 to 2 is equal to T from 1 to 2. Change in kinetic energy from point 1 to point 2. Now, point 1, let me draw this. We start from somewhere here. Let me see if I can. I try to draw this. We start from somewhere here. Right, is s equal to -1, and then point 2 is when we are at s equal to 0. I'm doing my best to draw something. I can think about it this way. This is where this is, let me see if I can draw. This is s equal to 0. and this is S equal to -1. So we go from 0.1 to 0.2. Right? This is 0.1, this is 0.2. And the spring is compressed and it's stretched. So U from 1 to 2, right? We have two forces. Well, we have the weight there. We have to take into account. We have the spring there. There is no other force, pretty much. That integral, we don't need to be worried about calculating it. If we had friction, though, that you'll see in the next problem, I'll talk about friction, then you have to calculate that integral f dr. In this case, two forces we're concerned with, spring and weight. So U from, that's supposed to be, so let's say U from 1 to 2 for gravity is minus mg delta H, right? And H being, we go from this point to this point. With the danger of making things crowded here. This is delta H. All right, they go from this point at this to this. In this triangle, right, we know, let's draw it here separately. In this triangle, we know this is 1 meter. Right? It's going down 1 meter. This angle is 20 degrees. So we are looking for delta H. And delta H being, that becomes 1 sine 20 degrees. It's one, you can start from the definition of sine. Sine is equal to opposite over hypotenuse, right? Delta H over 1, and then delta H becomes 1 sine 20 degrees. Now we're going downward, so this delta H is negative. So that becomes minus mg minus 1 sine 20 degrees. So this becomes, let's just leave it as that. This generally becomes positive, and it should be positive. If we go back to here, I said negative if the height increases, positive if the height decreases. Since we're going down, it should be positive. Just double check your final answer there. So that's for gravity. Work done by spring, 1 to 2 spring, I represented that way. Minus 1 over 2 k s2 squared minus s1 squared. K is given, right? We know that K is 20 Newton per meter. S2 and S1, what is S2 and S1? Can someone tell me what is S2 and what is S1? It's all about identifying the parameters, correct?
Would S1 be 0 and S2 be 1 meter?
All right, so let's look at where we are at the beginning and where we are at the end of this motion, right? That's what it matters in energy methods. Usually the path that you go from 1 to 2, when there is no, we'll talk about that, when there is no non-conservative force, it doesn't really matter. In this case, there is no friction, so the path doesn't matter. All it matters is that where you are at the beginning and what are the velocity, height, or information about you need information about point 1 and information about point 2. So in this case, let's see where we are. At point 1, if this is S0, right? If this one is S equal to 0 and S equal to minus 1. At point 1, you are at S equal to minus 1, right? So here's your S1 is minus 1. And remember, we are talking about how much the spring is stretched or compressed. If the spring is unstretched at S equal to 0, it means it's compressed 1 unit when we are up 1 unit, right? So S is equal to minus 1, right? Or 1. You don't need to even be worried about positive, negative because this is squared. So the amount the spring is stretched or compressed is 1. Just let me use positive so things are not, we don't need to be concerned. This is squared. So you care about how much the spring is stretched or compressed. It's compressed 1 unit. When you get to S equal to 0, the spring is unstretched. Right? And that's where you are at 0.2. So S2 is 0. Does that make sense to everyone? Any question on this one? Right. We care about how much the spring is stretched or compressed at that specific point, the beginning or end of the motion, right? Or the beginning and end of the motion in terms of what we are studying. Right? Motion continues, obviously, so that's not end of the motion. It's the point that we are interested in. So 2 points that we're interested in, first point and second point. We care about velocity at those points, usually height at those points. We care about, in this case at least, we care about how much the spring is stretched or compressed. So when we compress this, when we go up 1 unit, spring is compressed 1 unit because at S equals to 0 is unstretched. And when we're at S equal to 0, spring is not stretched. So S2 is 0. So this becomes minus 1 over 2 K, which is 20, times S2 is 0, so it becomes minus 1 squared. Right? Becomes 10, basically. I don't know what was I doing last time, that which part did go wrong. That all right, things like it's working this time. Second time the charm, apparently, not third. Hopefully, we'll see. So T from 1 to 2, right? That's just all the work. The only 2 forces we had that they're doing work are just there's a spring force and gravity. Then for kinetic energy is 1 over 2 m v2 squared minus 1 over 2 m v1 squared. Now, we push the mass up and we release the mass, right? That means the initial velocity is 0, which means this term becomes 0. So this becomes 1 over 2 m v2 squared, which is what we are trying to find. You know, we want to find what is the velocity at point 2. So just putting everything together, right? Let's put everything together. You'll get mg sine 20 degrees plus 10 from that one is equal to 1 over 2 m v2 squared. So from there, v2 is equal to whatever the value is. We have this m2, right? M is given as, tell me I gave you m. It is 5 kilogram. So we can replace this as also 5 kilogram. I forgot to put it there. Then v2 becomes, let me look at my notes. Well, that's the only unknown there, so just should be straightforward to do that. And the value for v2, I found 3.27 meter per second. Right. Minus 10. Well, this, remember, this is squared is for S1. So the negative behind S1 is still there. This minus is still there. So this becomes minus 1 squared. You can even put negative 1 inside. It doesn't matter. As I said, stretching or compressing doesn't matter. You can always use positive to avoid that. That's actually good. Good thing you brought up, because I was gonna get to this point that I am gonna emphasize over and over. When you are using energy method, the process is typically straightforward in most problems. What is gonna make it confusing and what is gonna throw you off? That obviously you'll see problems that they move things around, they are throwing things up, throwing things down, there's a spring, stretch, compressed. It's all about being patient and look at the signs, positive, negative. That's where I've seen probably 90% of the mistakes happen. Right? To be very cautious about every parameter you plug in. Should it be positive or negative? For the weight, work done by weight, I told you specifically if you're going down, it should be positive. If you're going up, it should be negative. So that's a checkpoint that you can check. Spring, be very, very careful about where you are at the beginning, where you are at the end. You don't care about what is going on in the middle, right? In so many cases, as long as there is no friction. If there's friction, you have to pay attention to that just for friction. But for spring, pay attention to how much is it stretched or compressed. If it's unstretched, then these S values at 0.1 or 0.2 is 0. S is how much the spring is stretched or compressed. Now, because it's squared, it doesn't matter stretching or compressing, right? You just have to put the magnitude there. And pay attention to a negative sign between and the negative sign in the back, which apparently I even forgot to put the equation I was talking about it. Which shows how common is that. I can tell you with confidence that a lot of mistakes in the next exam we're going to have on energy methods are going to be specifically because of these sign problems. So be very patient with this and pay attention to the sign and where you are and if it's negative, positive. And it's not uncommon to make mistakes about those, all right? Just practice and practice, I guess. That's all I can tell. And pay attention to signs when you're solving problems in this method, using this method. All right, let's look at any question on this one before I move on.
Can you quickly go over why you put position 1 and 2 like that instead of like the opposite way? Since in the problem statement they said it moves up.
So think about when the motion is happening, right? What is happening? The problem is telling us we are stretching, we are putting the mass at position s equal to -1, and we are releasing it. What would you get if you go the other way around, though? You don't have that much information about what happened. Okay. Let's say you assume you take where you are as 0.1 and where the spring is stretched all the way up as 0.2. Right? Then what are you trying to find? Then the moment that the mass is passing through s equal to 0 would be 0.3. You see what I'm trying to say there? Think about the sequence of the motion. We have a mass here, spring is unstretched at s equal to 0. We push the spring or push the mass up, we go to a point, right? So this is the second thing that happens, and then we let it go, or they let it go, and then it starts sliding down. There is a sequence of moves. Right? Now, that one to that one, pushing it up, there is nothing we can calculate there. Right? We don't know how much force is used to push this up, and we don't even care about it, right? Remember, energy method is all about finding a relationship between position and velocity most of the time. As long as there is no friction, we don't even look at a lot of details of forces and how do they interact with our mass. But you can try it that way, and you don't really get that much out of that. There is really not that much to calculate, I would say. I've never actually thought about it that way. That's how I can, I guess, justify this, or at least that's how I can explain this. But the motion is happening from when we are at the top and when we get at this point, because that's where we want to find the velocity. Right? It really doesn't give us anything. If the question was like, we are at s equal to 0, spring is unstretched, we hit this mass and it goes up. We want to find out what is the velocity of the mass when it's going up and compressing the spring. What is the velocity of mass after 1 meter going up? That would have been the case that you're talking about. Position 1 would be where we are in a stretch. Position 2 would be where the mass is when it's going up 1 meter, right? It's 1 meter above where it is, and we wanted to find the velocity at that point, right? While it's going up, it's stretching, it's compressing the spring. We want to find the velocity at that point. But in this case, we are looking for when it's released, it's taken all the way up and it's released from the top. So pretty much the logic tells us that that's the part of the sequence of moves that we have to follow. I guess that's the best way I can think about it. All right. Let's look at one question with gravity, with friction, because that's something that is a different story. That's the kind of problem that specifically or for this section before we start talking about conservation of energy conservation. All right, so let's say we have a, let me double check. Yeah, this is a good example. Let's say we have two boxes. This case, we have a system of two mass. We have this one, M1, let's call this. It's this way, and then it's on the ground. It's attached to another mass using a rope and a pulley. Pulley here is, so we go downward, and let's put a mass right there. M2. Now this is, I think, 4 kilograms. I can write probably a little better, 4 kilograms, but no guarantee. Yeah, making life difficult. 4 kilograms, and this one is supposed to be 20 kilograms. The problem statement, well, basically it's a system, let's say the system is released from rest. From rest. Well, this doesn't end here, obviously, it continues. The 4 kilogram mass slides on the surface with mu k, right? Coefficient of kinetic friction is 0.4. Find what do we have to find? Find the magnitude. Find the magnitude of velocity of masses when the 20 kilogram mass has fallen, I think so, yeah, has fallen 1 meter. All right. So we have a system of two masses here. It really doesn't matter by the end of the day as many masses we can have. You know, you can have so many masses in the system. Just you have to look at each when you're calculating potential work done by the system and change in kinetic energy. Just make sure that you take all of them into account. So previously we're looking at just one mass, so you take into account the velocity, initial velocity and final velocity of one mass. work done on that mass by different forces in the system. Now you have two, so when you calculate the work done, you have to calculate work done on both by all the forces in the system, and you have to calculate the velocity of both, take into account the velocity of both when you're writing the right side of the equation, or kinetic energy. So starting from what we have to form, this equation. Right? You have to form using energy method. We want to use the principle of work and energy and figure out what is the velocity. What is the hint that you have to use energy method? It's asking about velocity. Keep in mind, when we are using energy method, we only find the magnitude of velocity. But really, as you see, velocity is squared. So it's not like Newton's method that you can represent the velocity as a vector and have, or acceleration as a vector and have its ij components in Cartesian or different, or r theta components in polar coordinate systems. You don't really have the luxury. You do not have the vector representation of your velocity. Right? This is an energy method. We only care about the magnitude of velocity, or that's what we actually can work with. So keep that in mind. This is also another distinguishing point between which method to use. If you're asked to find the velocity vector, in this case, maybe you can probably guess it based on the direction of the motion. But typically, that's where you actually have to go back to Newton's method, right? Or we'll see later on, if it's an impact, you can still use energy method, but that's a different story. All right, let's stick to this. Magnitude of velocity, asking for velocity. So that's a sign that probably energy method can be helpful for us and make our life all easier. So let's start with work done, 1 to 2. Right? There is no spring. There is friction though, so we have a friction here. Just want to point that out. This is mu k. Making it worse or better. So many cases, I'm never sure. I don't. So it's friction there. Just keep that in mind. So we have two masses. Now, mass 2 is going down, right? Remember, the problem is saying when a 2 kilogram mass has fallen 1 meter. So the story is that this is going down 1 meter. I could probably do a little better, but that'll do. So this is going down 1 meter, which means this one is also moving 1 meter. So that's the story. That's the motion that's happening. Now, the top one, mass 1, the height doesn't change, so no work done by gravity on that one. The bottom one, the height changes 1 meter. It's going down, right? So some work done by gravity because we see change in height. So u from 1 to 2 gravity would be, oh, mass 1 doesn't give us anything. So that would be m2 g, and it's going down. I can always put the negative here and then say delta H would be -1 because it's going down 1 unit. Or if you feel confident, just put m2g delta H because it's going down. Remember that should be positive. Again, going back to what I said here. Right? Positive if the height decreases. That's the case for now. Becomes m2g. That's pretty much it for gravity. We don't really have any spring in the system. So that's that. We are still calculating the left side of the equation. Now, the one thing you have to pay attention here, now we have friction. Now, what is friction? Well, friction is the external force doing some work. It's not like the other two forces that we introduced here, done by gravity and done by spring. We don't really have a straightforward equation for that. So we have to go back to the integral form of the equation. right? Force due to friction, dot product, the motion along the path. So I have to actually write it this way. So U from 1 to 2 for, I don't know, just put it friction, I guess, for IC, just to distinguish that, is the integral from position 1, R1, to R2. In this case, I only deal with the force, friction force. So I'm going to put friction force. Fk dot dr. Right? Now, here goes the tricky part. Well, we know R1 and R2, right? This is point 1. This is point 1. This is point 2. So that's the motion starting from 1 to 2. The distance it goes from 1 to 2 is 1 meter. So we can say R1 is 0, R2 is equal to 1 meter. That's the limit for the integral. You don't need to put the unit there. That's that. That's the change is 1 meter, the motion. Now, remember, dot product. This is friction. I'm going to draw it here. This is your friction. Fk. This is your dr. It's changing in this direction, dr. It's going from 1 to 2 in that specific direction. Point 1 to point 2, which is from 0 to 1, basically. Now, dot product, that's why it's important. Now these two are in opposite direction, right? Fk is acting to the left, dr is to the right. So the angle between these two is 180 degrees. So this by itself becomes Fk dr cosine 180 degrees. When I was talking about dot product here, there you go, right here, in this note that I put there, A dot B is AB cosine the angle between these two vectors, and dr is to the right, Fk is to the left, the angle is 180 degrees, so that we have to take into account here. So cosine 180 degrees is -1, so we're going to get a negative there. That would be negative. And then this is going to be from 0 to 1. Fk, well, Fk is mu kn, right, in this case. So mu kn dr. Mu kn is constant, you take it out. Integral from 0 to 1 dr is basically 1. And I just write it here in case you want to later on follow steps. Dr. Integral dr from 0 to 1 is basically just 1. It becomes r from 0 to 1, 1 minus 0. So this becomes minus mu kn. These forces, force like friction is called is non-conservative force, and usually they are more challenging to take them into account. You have to pay attention to what is the force magnitude in this situation. In this case, it's pretty easy. This is m mu kn. N is you can also write it here. I'll write the next step. For now, n or whatever n is. All right, so this is the work done by all the forces. The right side of the equation, right side, 1 over 2, 1 over 2 m. Let me write it this way, actually. So later on, you know where does that come from. So t from 1 to 2 is t from 1 to 2 for mass 1 and t from 1 to 2 for mass 2. For mass 1 over 2 m1 v 1 squared. Oh, well, let me. v2 squared minus v1 squared. And for the other one is 1 over 2 m2 v2 squared minus v1 squared. Let's be cautious about this v, because later on we're going to use v for kinetic energy. All right, so, and I use v1 and v2 because these two masses are attached to each other, so they have the same velocity. So you can actually write this one like this. So t from 1 to 2 is nothing but 1 over 2 m1 plus m2 v2 squared minus v1 squared. All right, I just take into account all the masses in the system. This part is just because I said, well, they're connected, they move with the same velocity, they move with the same, they're attached to each other. So I'll just use, just add them up pretty much. Add these two equations together, you'll get t from 1 to 2. Now, again, it says it's released from rest. So v1 is 0 there. Once you get these two, the rest shouldn't be that bad. Right? Just put everything together. It's going to be m2g. They're forming this equation. m2g minus mu k. I'll just put n, then I'll plug that in. Is equal to 1 over 2 m1 plus m2 v2 squared. Now n, well, is m for m1. If it is m1, it's m1g, and this is n1 n. Let's put it this way, and I'll put I don't know what it's n, and I put friction here, fk, and you also have t there if you want to just quickly draw the free body diagram. N is m1g, so I'll just plug that in. It's always good to look at it, not always it's m1g, right? If I was on a sloping surface, then the story would have been different. Would have been probably m1g sine theta or cosine theta. So do not just plug in mg immediately. Quickly look at the free body diagram and figure out what is n, normal force in that case. So only thing missing in you know everything. You know m1 is 4 kilograms, m2 is 20 kilograms, you know m1, you know g, mu k is given 0.4, m2 is 20 kilogram. So pretty much you know everything except velocity. So v2, you can actually find it, right? Just, if I want to write in terms of, it becomes 2 times m2g minus mu k m1g divided by, this goes that side, and this is going to be m1 plus m2. So you can find your velocity. That'll be, I got it right here, 3.878 meter per second. That would be your velocity. All right. So many steps that things can go wrong. That's all I can tell you. All right. Look at both sides of the equation. Work done, kinetic energy, energy change in kinetic energy on the right side, work done on the left side from 1 to 2. Pay attention to where you are at point 1, where you are going to end up at point 2. Look at velocities, change in heights, if there is any spring, stretched or compressed, how much. If there is friction, that's the point for this example. Pay attention, you have to actually write the integral form of the equation for that. We don't have a very straightforward equation for this, and you see the reason, because this dot product, depending on what is the angle between friction and the path, can be a little tricky, and you'll see even later on when we deal with other things, other forces, like maybe not in this specific section, but a rope or something like a chain. That direction can be tricky, so you have to pay attention to the direction, dr, and the angle between that and the friction force. Right? And that's where the dot product helps you to figure out if it's positive or negative. As I said, positives and negative signs are the main things that you have to be careful about when you're using energy method. Aside from the fact that it's probably less comfortable for a lot of us because we've been dealing with Newton's method for a while, and now this is just somehow a new approach, totally new approach that we have to get comfortable with. So, question on this one, right? Did it make sense what happened there, the process? Anything that was confusing there? All right, so let's do an example that has both spring. We did a spring and a mass, but let's do something that's a little more interesting with the spring. I just want to make sure that the stretching and compression is there and it's happening. Right? You get it. So let's do this example. Let me look. Yeah, this is good. Let me draw this here. We have some interesting stuff going on. We have this color here that is at this point at the beginning, and it's at this point at the end. It's the same color, but somehow I'm changing its dimension. It's here at the end. And then it goes through a rod, or this is as good as I can draw this. Hopefully it makes sense. Let's do, somehow I did the same thing. So let's do this. Right. These are just two. We have a point, let's say point, there is a support there, and we have a spring that is attached to this, and then it comes to this point. This is your point 1. This is your point 2. Dimensions. This one here is 200 millimeters. This one right there, you can draw a straight line in this direction. So this one right there is 250 millimeters, going from point 1 to point 2. So we have a color. Let me write the problem statement. The 4 kilogram color is released from rest at position 1. Right. Let's just add this to make sure that on the smooth, meaning that don't worry about friction at this point, smooth bar. If the spring, we know the spring constant, if the spring constant is K is equal to 6 kilonewton per meter, and the spring is unstretched in position 2, right? So when we get to position 2, it's in its natural length. The question is, what is the velocity of the color when it has fallen to position 2? Take it to position 1, we let it go, right? It starts accelerating, it comes down, both because the spring is basically pulling it, because at that point the spring is a stretch, so it's trying to go back. Remember, a spring is always trying to go back to its natural length. If it's compressed, it's trying to stretch itself. If it's a stretch, it's trying to compress itself to go back to its natural length. So both because the spring is pulling it down, it's trying to go back to its natural length, and also because of its weight. Now we're asked, given the information and the geometry of this problem, we're asked to find what is the velocity of this color when it passes point 2 or position 2. It may not stop there. It might still go down. It will go down, obviously, not may, definitely. All right. So again, u from 1 to 2. This is playing around with the geometry a little bit. If I can write normal u here, u from 1 to 2 is equal to 2t from 1 to 2. All right. In terms of, well, there is no friction, so that you can be you can feel good about it, I guess. Don't have to deal with that integral. U from 1 to 2, we have those two forces, right? Now, let's see. Let me start with, I think it's better to start with gravity. From 1 to 2 gravity, U from 1 to 2 spring. And let's use M so we can, I don't know. So what is the U 1 to 2 for due to gravity, or work done by gravity? I was going to ask you about the spring, but gravity is the easy one.
Negative mg delta H.
Well, then what is H, and what is the final number, at least in terms of
50 millimeters.
Say it again, right?
250 millimeters.
Then, so we have minus mg delta H. It's minus mg. H is 250 millimeters. Let's convert that to, what happened?
Negative 250.
Negative 250, exactly. So that becomes minus, I'm going to convert it to meter. We're going down. So this 25. This becomes M is 4 kilograms. Right? M is 4. G is 9.81. You do the calculation. You'll get about 4 times 1 over 4 is, it becomes 9.81. You know. Actually, not I never talked about the. It's. I should have talked about the unit at some point, did I? I think I never did. That's my. I should have talked. So what is the unit for work, guys? Work done. Go ahead. Someone said
Would
joule.
it be joules?
Joules, yeah. And basically joule is well, force times displacement, right? That's how we define this work, which basically Newton meter. So write it this way, Newton meter. Then you can define it whatever you want, but let's just stick to what that is. Right? It's force times displacement. Force is Newton, displacement is whatever unit you use for displacement. Here is I use meters, so Newton meter. Or joule. All right, so gravity one was the easy one. Let's do the spring. Minus 1/2K S2 squared minus S1 squared. Now, well, K is given, not a big deal there. Let's see, what are S1 and S2? S1 and S2. What is S1? Now, what is S2? Let's just start with S2. S1 is 0.2. Oh, that's one opinion. So let's start with S2. S2 is the easier one. What is S2? What is how much the spring is stretched or compressed at position 2? Nah. Look at the problem statement. Read the problem statement. No, not there yet. Yes, exactly. We got there. Thank you, someone. Yes. Thank you, all of you guys. Yes, S2 is 0, right? Because if you look at the problem statement, and you can actually, if you can read my handwriting, that the spring is unstretched in position 2. So we said S is how much the spring is stretched or compressed. So this is 0. Now, what is S1? Well, right. How much the spring is stretched in position 1?
Would it be like the hypotenuse minus S2?
Hypotenuse, well, S2 is 0, though.
Oh, well,
Mhm.
minus 0.2.
Minus 0.2, exactly. Yeah. And I think, yeah, it becomes 0.12, Richard. Yes. So I care about what is how much is its correct current length minus its natural length, right? That's how much the spring is stretched. So what is the current length is basically in that right triangle, 200 millimeters, 250, you have to find the hypotenuse. So that would be, I'll write it in millimeters, so it's easier to follow later on, plus 250 squared. That will give you the current length of the spring. Now, because you want to find out how much is stretched, you minus or subtract the natural length, which is 200 millimeters. So it gives you 120 millimeters or 0.12 meter. Stick to concepts and definitions. If you know what you're looking for, the rest is just paying attention to geometry and information you're given. Don't get tricked, right, by the way the problem looks. Remember, what is S? S in your mind, how much the spring is stretched or compressed. How do I find it? I need to find what is the current length of the spring minus what is the natural length. That tells me how much the spring is stretched or compressed. How do I find the current length of the spring? Well, I'm given the information, the geometry, 200, 250, so I can find the current length of the spring. Minus what is the initial length or natural length? I'm given that too. It's unstretched in position 2. When it's in position 2, the length of the spring is 200 millimeters. So current length minus unstretched or natural length, spring length, or the length of the spring in natural position gives you how much the spring is stretched or compressed. That's what I wanted to talk about in this problem. Now, the rest is hopefully pretty straightforward. Change in kinetic energy would be 1/2 m is only m. It's released from rest, so we only have final velocity pretty much, right? Actually, let me do the calculation here. So this is equal to, once you know S2 is 0 and S1 is 0.12, that will give you, let me see if I have 43.31 Newton meter or joule as work. Knowing these two and the kinetic energy, that is going to be V2 squared minus V1 squared. Again, it's released from rest, so that at the beginning velocity is 0. This becomes 1/2 m V2 squared. Right? Now, knowing these two, pretty much you can star and 2 from. Let me use this space. You're gonna hate me for squeezing everything together, but I just don't want to go to the next slide. From this and this, right? You can form the general equation that you're looking for. So that becomes 43.31 plus 9.81 is equal to 1/2 m V2 squared. M, also we know m, I should have probably plugged that in. Tell me I gave you like 4 kilogram. Yeah, that's 4 kilogram. Plug in the 4 kilogram value there. V squared, V2 becomes 5.15 meter per second. Velocity at point 2. Right. Stick to definitions. So whenever you feel like things are confusing, go back to what was the equation, what was the definition. Right? Problems, they give you random information here and there, they twist the sentences. Dig a little deeper and go back to definitions sometimes and make sure that you actually are doing what you're supposed to do. Don't just plug in random numbers from here and there. All right. I have 10 minutes and I want to squeeze in one more example. I think there is not that much new in that problem, in that example, but I just want to do one in 3-dimensional space, a simple one, obviously. And you'll see that it actually makes your life, I think, much easier when you actually use energy method in those cases. Any question on this one before I move on? All right. Let's do this one. I will do my best to. This is X, Y, and Z. And we are going from point 1 to point 2. And then just let's put some mass there, right there, like this, attached to spring. and I'll give you the coordinates for each. Point 1 coordinate is 1, 1. One, 1, 0. Point 2 coordinates is 4, 4, 2. Where the spring is, this point is 6, 2, 1. Just coordinates in three-dimensional space. We're going from point 1 to point 2. M is 10 kilogram. It's a color. It goes from point 1 to point 2 on a smooth bar, right? M, I'll just, and it goes from position 1 to position 2. Excuse my writing at this point. Gets worse closer we get to the end of class. So the it's going from 1 to 2. The spring K is equal to, for the spring, or spring stiffness, spring stiffness K is equal to 100 Newton per meter, and the unstretched length of the spring is 2 meters. Find the velocity of that color at point 2. Did I say did not mention that it's released from rest. At this point, you know what I'm trying to say, hopefully. Basically, I'm trying to say is that no initial velocity. All right. So I'm doing what I did before. I was doing before, right? Nothing surprising there. And U1 to 2, well, basically we have a spring and we have a mass changing its height. So we have two types, 1 to 2 gravity, 1 to 2 due to spring. Now, for height, let's say minus mg delta h. It is in three-dimensional space, but it shouldn't really throw you off. All you care about is change in height, and that's your y direction in this case. So you're going from y equals to 1 to y equals to 4. As I said, if you have no friction in the system, you don't care about what is happening in between. Right? That's the beauty of energy method. You only care about the beginning and the end, as long as there is no non-conservative force like friction in your system. So that's become minus m g 4 minus 1. Right? The height at the end minus the height at the beginning. If you plug everything in here, you'll have m as 10 kilogram. 10 kilograms there, g is 9.81. So you do the multiplication, this becomes 30 times, I can do it in my head. It becomes minus 294.3 Newton meter. Right? Did that make sense, guys? It is three-dimensional space, but still you only care about changing height. And your height is in y direction. So that's pretty much it. Let's figure out the spring. 1/2k S2 squared minus S1 squared. Now, what are S1 and S2 here? What is S1 and what is S2? What is S1? And here where we are at the beginning, right? This is where we are at the beginning of the motion. This is where we are at the beginning, and this is where we are at the end. Remember what S is. How much the spring is stretched or compressed. So what you need to know is what is the length of the spring at that given position or that point minus the unstretched length of the spring. Now, previous example was in two-dimensional space, right? So we could calculate it. We found the length in two-dimensional space, like the length at that position minus the unstretched length. Here we just expand it to three-dimensional space. You have 2 points. You have the initial point right here, and one end and the other end here. So you are basically finding the distance between two points in three-dimensional space. Right? Well, how do we find the distance between 2 points in three-dimensional space? Right? We just square root of the difference between each component squared, right? For both. So I write it this way: 6 minus 1 squared plus 2 minus 1 squared plus 1 minus 0 squared. This is the length of the spring at position 1, from where the origin to position 1. Now this, you are looking for S. So this length minus the unstretched length. Unstretched length is given to you directly, it's 2 meters. So this is minus 2. That's it. That gives you S1. Same story about S2. The length of the spring when you are at point 2. Between these two, you have 2 points, so you just find the distance between these 2 points in the three-dimensional space. That would be 6 minus 4 squared, right, plus 2 minus 4 squared plus what else we have to, 1 minus 2 squared, or 2 minus 1, it doesn't really matter since we're finding out, minus unstretched length. Okay. So the story is the same. I just changed it into three-dimensional space. All you need to do is just find the length of the spring at that position minus what is the unstretched length of the spring. That's how you can calculate how much the spring is stretched or compressed at a given point. Don't care what's happening in between. So the answer to these would be, if I did not make any mistake, 3.2 meters, and that one would be 1 meter. T, the easy one is pretty much is 1/2m v squared. Let's just put, sorry guys, I know the time is up. Just give me a minute or two, just wrap this up. If I can draw a normal looking parentheses, v2 squared minus v1 squared. I told you it's released from rest, so at this point should be pretty comfortable identifying that. This becomes 1/2m v2 squared. So putting everything together, I'll put it here. You have u from 1 to 2 is equal to t from 1 to 2. So you have minus 1/2 K S2 is 1 squared minus, S1 is 3.2 squared. And that one would be minus 294. 294.3 is equal to 1 over 2 m v2 squared. And you know also K is given to you directly, it's 100, M is given to you 10 kilogram. So only thing missing in this equation is just V2. So V2 becomes, if I did my calculation right, 5.77 meter per second. Double check these numbers. I think it's correct, but double check. All right. Kept you